Hi, this is the video for section 2.1 of A Student's Guide to the Schrödinger Equation. This section is all about operators, eigenvectors, and eigenfunctions, and I find that some students react to the words quantum operator with a little bit of trepidation. But you've seen operators before. The couple of examples I talk about here are the square root operator or the take the first derivative with respect to x operator. In other words, operators are just mathematical instructions to do something. I do mention here that operators that you're going to run into in quantum mechanics are linear, and I talk about two of the characteristics of linear operators here and here. You may be familiar with these, so I'll go through them quickly. The first is, if I have two functions or two numbers that this operator is going to operate on, if I add them together and then operate, I get the same answer as if I operate on one and then operate on the other and then add those two together. Now clearly, the square root operator, for example, operating on numbers, does not fall into this linear category. Good example of that. If I take the square root of two numbers, say 9 and 16, if I add those together, I get 25, and I take that square root, I get 5. But what if I take those square roots individually? Square root of 9, and then I add that to the square root of 16. Well, we know the square root of 9 is 3, and the square root of 16 is 4, so this turns out to give me 7. In other words, adding before or adding after the operator is applied makes a difference in the outcome. So, square root, not a linear operator. Let me clean this up a little bit before we talk about the next characteristic. So what about this multiplying by a scalar? Does it matter if I apply the operator before I multiply? Well, if it's a linear operator, it does not matter. But let's use our square root example. Imagine that c is a constant that is 4, and f is a number, in this case, say 9. Then if I take the square root of 4 times 9, that's the square root of 36, I get 6. But what if I pull the constant out and say, okay, I'm going to take 4 times the square root of 9. Well, you know that 4 times the square root of 9 is 4 times 3. That's 12. So clearly, the square root operator doesn't obey the rules of linearity in terms of multiplying by a scalar as well. Okay, so linearity is fairly straightforward. To really understand operators in quantum mechanics, it's helpful to think of the operator as a matrix and think about what happens when you multiply that matrix by a vector. So, I'm going to write a matrix with these two bars over its head. So R is a matrix here. It has these 4 elements. A is a vector. It's a column vector here. It has 2 components, A1 and A2. Now, I hope you remember how to multiply matrices, or in this case, a square matrix times a column matrix. R11 times A1, and add that to R12 times A2. There's what that gets us. Now, take the bottom row, multiply that by A1, this by A2, there's the second one. So let's clean this up again and look at what we've got here. This is a vector. This is one number on the top, one number on the bottom. That's a 2-element column vector. So what happened by applying our operator, our matrix in this case, was we turned one vector into a different vector. That's why you'll see this sometimes described as not just a linear operator, but a linear transformation. It transformed one vector into another. Okay, what does that really do to that vector? To understand that, I think it's really helpful to see a concrete example. So I made up this matrix R, which has these 4 elements. Let's see what it does to a vector. Here's a vector. We'll take this guy, A, which I just call 1, 3. That is, A sub x is 1, A sub y is 3. So there it is. 1 step in the x direction, 3 steps in the y direction. Let's apply our matrix R to that. Here you see the math, the multiplies happen, and you get this new vector, minus 2, 10. Minus 2 in the x direction, 10 in the y direction. That's this guy, which I called A prime. So look at what applying our matrix to this vector did. It not only changed the length of the vector, small to big, it changed the direction of the vector. And in general, that's true. Pick a random vector in a random matrix, chances are applying that matrix to the vector will produce a new vector with a different magnitude and a different direction. And why does it do that? A little explanation here. it points out that the new vector, A prime in this case, is a weighted combination of both components. That is, the x part of A prime involves both the x and the y part of A. Likewise for the y part of A prime. So you would expect that the magnitude might change. And as it says down here, if the ratio of the new components differs from the ratio of the original components, then the new vector points in a different direction from the original one. So the relative amounts of the basis vectors are changed by the operation of the matrix. As you can imagine, this is going to come up big in quantum mechanics when we're dealing with functions and eigenfunctions, waveform solutions to the Schrödinger equation. That's why we're emphasizing this now. Okay, so let's consider the effect of R on a different vector. Here's a vector I plus j hat. So in other words, one step in I, one step in j. There's vector B. What if I apply our matrix R to that? Well, we do the multiplies, and look what we get. 2 over 2, or pulling the common factor of 2 out, 2 times 1, 1. But 1, 1 was just our original vector B. So in other words, applying the matrix gives us the same vector back, except twice the magnitude. Here's a graph of it. That was the original B. It's kind of faint and it's behind there. That's the original B. Here's the B prime. Twice as long, but same direction, because the ratio of the components is the same. So applying the operator in this case changed the length, but not the direction of B. You're probably ahead of me. What we have here is an eigenvector of the matrix R. And that factor of 2 by which the magnitude was scaled, that's the eigenvalue for that eigenvector. You say, yeah, but what if it had neither changed the length nor the direction? In that case, the eigenvalue would have been 1. Okay, so B equals I plus j, that is, one step in x, one step in y. That is an eigenvector of the matrix R with an eigenvalue of 2. And we can write that as a general equation. Here it is, R the matrix times some vector A, if it equals lambda, which is a constant, times A, then you have A as an eigenvector of R, and lambda is the eigenvalue. If you haven't seen this before, or if you have, you may be wondering, how do I find those eigenvalues and eigenvectors if I'm given some random matrix? Not too difficult. There are several ways to go about it. You can see some procedure on the book's website if you're interested in that. And if you work through that, you'll see that another vector, which I called C, I minus j hat, is actually an eigenvector of the matrix R as well. And in that case, it has an eigenvalue of 6. That means it grows by a factor of 6 when we apply the matrix. A couple of helpful hints here. The trace of the matrix, that is the sum of the diagonal elements, turns out to be 8 in this case, is the sum of the eigenvalues, 6 and 2. And the product of the eigenvalues, which is 12 in this case, 6 times 2, is the determinant of the matrix. If you don't remember how to do the determinant, it's very straightforward. You take these two elements, the diagonal elements, and multiply them. Then you take these two cross-diagonal elements, multiply those, and subtract them. So you get 16 minus 4 in this case, which is 12, which is also 6 times 2. Okay, in quantum mechanics, we're really interested in operators that operate on functions, and we can write an eigenvector or eigenvalue equation just like we did for matrices and vectors using functions. So here's an operator O with its little caret hat, not meaning unit vector, meaning operator, times function psi gives us lambda times function psi, just a multiple of that same function. So what kind of operator gives you the same function back? Well, let's try some. Let's take the derivative operator, the derivative with respect to x, and we'll feed it a function, sine kx. Let's see what happens. When we apply that operator to that function, we get the derivative of sine kx, which is k cosine kx. Does that equal some constant lambda times sine kx? Well, just imagine a few values of kx, such as 0 and pi. Plug those in here. You're going to get 0 on this side. There's no lambda that we can use to turn that into the values of cosine of 0 and pi. So clearly, no lambda works for this. That means that sine kx is not an eigenfunction of the derivative operator. But what if we take a second derivative operator? Notice this does not mean you take the derivative and then get a result that you square. It means you take a first derivative and then you take a second derivative of that result. So here we are taking the second derivative of sine kx. The first derivative gives us k cosine kx. Take another derivative, that gives us a k squared, but also a minus sign because we're going from cosine to sine. So the question is, does this ever equal lambda times sine kx? Well, sure it does, as long as lambda is equal to minus k squared. So sine kx is an eigenfunction of the second derivative operator with respect to x, and the eigenvalue is lambda equals minus k squared. All right, main ideas of this section. Linear operator can be represented as a matrix that transforms a vector into a different vector. If that new vector is a scaled version, you have an eigenvector, and the scaling factor is the eigenvalue. You can do the same thing with functions, and in that case, if you get a multiple of the original function, that function is an eigenfunction of the operator. And in quantum mechanics, every physical observable, position, momentum, energy, angular momentum, is going to be associated with an operator. And you can represent the state of a system as a linear combination of eigenfunctions of that operator. The eigenvalues for those eigenfunctions are going to turn out to represent possible measurement outcomes of that observable. All right, there are some really beneficial things you can do with using Dirac notation in operators. We'll see those in the next section.